Imagine peering into the depths of the universe, unveiling secrets previously hidden from human eyes. Thanks to the James Webb Space Telescope, we've entered a golden age of cosmic discovery. Today, we're exploring the most exciting revelations from JWST on exoplanet atmospheres and habitability, the cosmic origins of galaxies, the mysteries of black holes, spectacular nebulae, and the very chemistry of distant worlds. Let's begin with exoplanet atmospheres, the veils that both shroud and reveal the true nature of distant worlds. In July 2022, JWST beamed back the first transmission spectrum of WSP-96b, a scorching, hot Saturn hundreds of light-years away. Water vapor, once just a theory for this world, was unmistakably present. Webb's sensitive vision also detected a surprising high-altitude haze, something even Hubble missed, proving that giant planets can cloak themselves in layers of obscuring aerosols. This haze insight is shaking up ideas of how atmospheres form and change, reminding us how much more there is to uncover. Next, consider WSP-39b, another hot Saturn. Webb's observations in mid-2022 offered the most detailed exoplanet atmosphere profile yet. Not only did we see a large carbon dioxide absorption feature and confirmed the presence of water vapor, sodium, and potassium, but for the first time ever, sulfur dioxide from photochemistry was detected. Why is this a big deal? It's the first clear proof that sunlight is triggering complex chemical reactions in alien skies, just like in Earth's own stratosphere. This molecular inventory is a triumph, showing off Webb's ability to reveal diverse molecules and even trace chemical processes on worlds hundreds of light-years away. Venturing closer to home in size, Webb targeted the TRAPPIST-1 system, an array of rocky, Earth-sized planets orbiting a nearby red dwarf. In March 2023, JWST measured thermal emission from both TRAPPIST-1b and IL-C. The innermost, TRAPPIST-1b, showed a broiling dayside temperature around 380 Kelvin over 100 degrees Celsius. The absence of significant atmospheric signatures suggests these rocky exoplanets lack thick atmospheres, perhaps stripped away by harsh stellar radiation. For TRAPPIST-1c, no evidence of a Venus-like blanket of carbon dioxide was found, indicating that even rocky planets in supposedly temperate orbits may be less habitable than first hoped. These measurements define a new era, actual, direct data on the temperature and composition of Earth-sized planets beyond our solar system. This is crucial, as it constrains where in the universe life-friendly worlds might really be found. But JWST's gaze didn't stop there. In September 2023, it studied the mini-Neptune K2-18b, which orbits in its star's habitable zone. The spectrum told a remarkable story, clear signs of both methane and carbon dioxide, fingerprints of a potentially water-rich, Hycean world, one with a global ocean beneath a hydrogen-rich sky. Even more tantalizing, a subsequent study in 2025 reported tentative evidence of dimethyl sulfide, a molecule that, on Earth, is almost exclusively produced by living organisms. While this possible biosignature is fiercely debated, it underscores an unprecedented power. For the first time, we have the tools to probe the complex chemistry that could point to life on temperate ocean worlds far away. Webb hasn't just studied exoplanets as mere points of light, it's begun to directly image gas giants themselves. Using advanced coronagraphs, JWST captured the innermost planet HR 18799e and directly detected carbon dioxide in its atmosphere, marking the first direct image of CO2 gas on an exoplanet. Observing this and other worlds like 51 Eridani Biahe shows that not only can design and formation models be tested using real data, but that the very building blocks of planets, elements heavier than hydrogen and helium, are spread throughout the galaxy, helping to piece together the puzzle of planetary birth. But let's zoom out to the whole universe. JWST identified a protocluster of 7 galaxies at a redshift of around 7.9, meaning the light left these baby galaxies just 650 million years after the Big Bang. This cluster, called the Pandora's cluster precursor, is direct evidence of how galaxies began to clump together early, forming the seeds of vast cosmic structures. Then, in 2024 and 2025, JWST spotted the most distant galaxies ever seen, JWST Z14 and Z14 just 300 million years post-Big Bang. The discovery of oxygen and heavy elements in these adolescent galaxies shocked astronomers. Metal enrichment, thought to take billions of years, happened in mere hundreds of millions. This means that the earliest stars were forging new elements at an astonishing pace, rewriting models of how galaxies and stars formed and evolved. One of the most surprising finds is the so-called Big Wheel galaxy, a massive spiral structure existing only 2 billion years after the Big Bang. Classic theories argued that gentle gas flows over billions of years were needed to build such organized disks. Big Wheel was already in place, suggesting that galaxies formed and evolved far more quickly and dramatically than we ever imagined. This relentless drumbeat of discovery has even landed squarely in one of the thorniest debates in modern cosmology, the Hubble tension. By measuring distances to galaxies using Cepheid stars, JWST confirmed a higher value for the Hubble constant, matching Hubble Space Telescope's results and deepening the conflict with the measurements from the Planck Observatory's map of the cosmic microwave background. The implications are profound. We may need new physics, perhaps early dark energy, or revisions to our understanding of cosmic expansion itself, to explain the difference. JWST is not only observing the universe, but forcing us to rethink its most fundamental laws. What about the monstrous engines at the heart of galaxies, supermassive black holes? In July 2023, Webb's spectrographs captured a 9 million solar mass black hole in the galaxy Sears 1019, just 570 million years after the Big Bang. Even more astonishing, in the famed ultra-distant galaxy GNZ11, JWST detected a 2 million solar mass black hole rapidly growing less than 500 million years after time began. These discoveries mean that black holes formed swiftly, in some cases either directly as large masses or by ultra-fast growth. Our timeline for the birth of these cosmic giants keeps getting pushed back, adding new urgency to big questions about their origin and influence in the young universe. JWST's infrared vision has also transformed our view of stellar birth and death. Its portrait of the pillars of creation, the towering, dusty columns of the Eagle Nebula, revealed newborn stars tucked within and behind the iconic pillars, formerly invisible to us. In the Carina Nebula's cosmic cliffs, intricate jets and outflows from fledgling stars are exposed, showing cosmic nurseries in action. In the Orion Nebula, JWST found free-floating Jupiter mass binary objects, dubbed jumbos, whose origins are mysterious. How could such planet-sized objects form and end up bound together, away from any star? This disrupts long-standing theories of how stars and planets take shape. JWST's prowess isn't limited to birth. It's documenting celestial death with equal precision. Its infrared image of the Southern Ring Nebula, NGSR 3132, peered into the very heart of a dying star's swirling shroud, revealing a hidden companion and intricate shells of gas. These details allow us to model exactly how stars shed their outer layers, recycling elements that will later become planets, and maybe life. Spectroscopy is JWST's ultimate tool, and it has already paid dividends. In 2025, using the MIRI MSS spectrometer, scientists finally confirmed the presence of crystalline water ice in the debris disk around the Sun-like star HD 181327, the first direct look at solid water in another system's protoplanetary leftovers. This confirms that the ingredients for comets and potentially habitable environments are common across the galaxy. Exoplanet atmospheric spectra now routinely show rich patterns of water, carbon dioxide, methane, sodium, and potassium, opening the door to someday spotting the signs of life, such as oxygen or ozone, in alien skies. Taken together, these discoveries are igniting a scientific renaissance. We're seeing that planetary atmospheres are more diverse and dynamic than imagined, that galaxies formed and died rapidly, and that the chemical and physical fingerprints of life's building blocks are widespread. JWST is more than a telescope. It's a time machine and a laboratory for answering cosmic riddles. Each new result challenges what we thought we knew and raises deeper questions. What worlds might host life? How quickly can galaxies and black holes form from chaos? How did the chemical complexity necessary for life emerge so fast? The universe is richer, stranger, and more alive with possibility than we dared to hope, and we are only at the beginning of this voyage of discovery. With every spectrum, image, and data set, the James Webb Space Telescope is rewriting our cosmic story. Never before has the night sky promised so many answers, and even more tantalizing mysteries.